So, having devised a kind of general relation to describe oscillatory motion and its special case, simple harmonic motion, let's play around these equations a bit. Let's devise a problem in mathematical terms. For example, let us take a situation when the force and displacement of a body are related by the equation F is equal to minus 5x minus 2 whole cube, where x is the displacement and the force acting on the body is F. Now, instantly you recognize this is not a simple harmonic motion, because simple harmonic motion is invariably the force is related to the first power of displacement. So, job is, this could be oscillatory motion or not. Now, the power 3 indicates that it could be simple harmonic motion. But one of the characteristics of simple harmonic motion is that force must be opposite to the displacement, no matter whatever is the direction of this displacement. So, is it satisfied in this particular case? Take x is equal to 2. When x is equal to 2, you find force is equal to 0. Put 2 here, 0. When x is greater than 2, say 3, then you can see that force is negative. 3 minus 2 is 1, let's say x is 3, so this side is positive, this whole thing is positive for x greater than 2, so force turns out to be negative or less than 0. If x is less than 2, say 1, 1 minus 2 is minus 1, minus 1 cube is minus 1, minus 2 minus is plus, so F is equal to positive or greater than 0. So we find that if you take a defining point 2, on the either side of 2, the displacement is exactly opposite to the force. If it is the right side of a point 2, that is x is greater than 2, the force acting on it is opposite, minus. If x is less than 2, which means left side of point 2, then the force is positive. It means point 2 is such a point which experiences no force. But on either side of this point, you have a force opposite to the displacement. What are you looking at? You are looking at a kind of simple harmonic motion around the point 2. Around the point where x is equal to 2. This is 2. Remember one thing. How do you find the equilibrium position given such an equation? There is a clue. At the equilibrium position, the force is always 0. Look at how have we deduced that the 2 is the point around which the simple harmonic motion is taking place, because at 2 the force is 0. We know that in the equilibrium position or the mean position around which the oscillatory motion takes place, the force is 0. So we tell that this is a simple harmonic motion around point 2. By the way, can we tell how far the body moves in either side of point 2? From this equation, we cannot tell. This is also called the amplitude. We cannot derive the amplitude from this equation. All we can tell that the force and displacement are so related, it will be an oscillatory motion because it is in the general relation of F is equal to minus k x to the power of n, where in the present case n is equal to 3 and k is equal to 5. So we say this is an oscillatory motion but not simple harmonic motion, and the oscillation is happening at point 2 in the x-axis. I'll tell you another way to visualize this. Replace x minus 2 with a new variable x. Let's call it capital X. Now this equation now boils down to f is equal to minus 5 x to the power of 3. It is easier now to visualize because this is in the form of equation k x to the power of n. This is a kx to the power of n, where k is 5 and x is remained as capital X. So this is a simplified version. But what exactly is replacing this variable with x minus 2? You can see this from this example. Suppose there is a coordinate system and there is a position of the particle P. This coordinate system let us call a small coordinate system x, o, y. Now let us get another coordinate system called capital X, O dash y, and let this capital X, O dash y be situated in such a manner that it is separated from O in the x-axis by a distance of 2. Now this point, let's call it P. The point P, a person sitting in X, O dash y reference frame, let us say that he describes point P as having coordinate x and y in his local coordinate system, x and y. The local coordinate system will be x, O dash y. As against this, the person sitting at O belonging to the reference frame x, O, y describes this as x and y in the original variable that we are familiar with. So a person sitting at x, O, y frame tells that this point is x and y in my coordinate frame. Now what is the relation between x and x dash? X and x, capital X. You can see that capital X is nothing but small x minus 2, because this coordinate system is nothing but it has been shifted by a distance 2. So the x coordinate of every point in the reference frame x, O dash y is nothing but 2 less than the x coordinate that will be described by an observer sitting at the reference frame x, O, y dash. It means if a body is executing simple harmonic motion back and forth in this reference frame, let's say in the x-axis, then the description of that oscillatory motion from the reference frame of small x, y, o will be nothing but x minus 2 in this reference frame. Meaning by the description of the oscillatory motion of this frame and the description given by this small x, o, y observer is related to this equation. F is equal to minus 5x cube is this reference frame where x is its variable and the simple harmonic motion being executed here. The same equation described in the reference from x, o, y is f is equal to minus 5x minus 2y. This is x, o, y reference frame and this is x, o, y reference frame. So you see, this equation is nothing but the representation of the same physical phenomenon occurring in another reference frame shifted by a distance of 2 along the x-axis. So you see, the abstract mathematical equations are actually related to the physical representation of reality. The only thing is that they help us in understanding certain aspects of physical reality which are not easily observable on the surface. For example, when somebody tells it is 5 into x minus 2 whole cube, you wonder what exactly are these mathematical terms. It is when it is decoded, you find that it is nothing but an observer sitting at 2 meter distance describing in his own language or his own terms a simple harmonic motion that is occurring at a distance, and the distance is 2 meters from its own place. It's all the same thing but a different representation of the same physical reality in two reference frames.